Okay, welcome everybody. You know where you are and who you are. A few administrative things real quick. Actually, I feel kind of naked without saying it. This is CS235 Applied Robot Design for Non-Robot Designers. This is lecture 14. So, I just emailed out some special notes for Lab 3 assembly. And because they're extremely important for your success or lack thereof, we're going to go over those real quick. Okay, the first thing is orders of operation is critical for this lab to work. Everything looks pretty similar, but they're actually very different, and none of the parts are interchangeable, not even one. So you have to assemble them in the right order, put the dowel pins in from the right side, the screws from the right side, and most of this is not symmetric, and dowel pin holes don't go in self-tapped holes, etc., etc. So to prevent this from happening, we're going to use a color coding scheme, and I'm really dead serious about wanting absolutely everyone to do this. So your part should look sort of festive and holiday-esque before we assemble them. So the blue holes, can everyone see the colors on here? The blue holes are what? The red holes are what? Self-tapped. And the green holes are what? Through holes. Yes, so blue holes are dowels, red is self-tap, and green is screw-through hole. I want you to do this on every part. I know it's laborious. I apologize for that in advance, but it's one of these things where an ounce of prevention will save you a shit ton of hardship. So the other thing is, you see this little pyramid here? I want that on all of your stacks, because what will happen is, if you come and show me and Rob, and I do want to see these, everyone before you assemble stack, Rob or I needs to check off to make sure it's in the right order, mainly because it's extremely difficult to get these things apart if you do it wrong. So once we've said, okay, you're good, you draw a little pyramid on it, and then if you happen to drop your parts by accident, and you put them back together, but you put them back together incorrectly, that no longer is a nicely formed pyramid, and it will easily show you that you're out of order. This is one of those things where before you assemble things, you really do want to check with Rob or me. The person to your left or right may or may not be assembling it correctly, and we don't want compound errors. So color code, the pyramid, make sure that you're inserting screws from the right side and not the wrong one. And another rule is, you know how a lot of these, the dowel pins are flush on one side for maybe these two, and flush on the other side down here? So you don't need to insert them from different sides. What you do is insert them all at the same time from one side, and then those that need to be flush on the other side, just pound through on the opposite way. Does everyone get what I mean by that? Okay, so those are two quick rules. Okay, we discovered in arbor pressing the flangeless bearings into these that it's really easy to get overzealous and crush the wood underneath, and then the bearings are cocked at an angle, and then your shaft doesn't go in. So I'm going to hide the arbor presses so no one's tempted. Also, that would be a logistic bottleneck in terms of, like, there's really one arbor press that would work well for this lab and many more of you. So I bought more rubber mounts, the good ones, and we'll be using exclusively rubber mounts. There are special tools I've made for inserting the bearings, and when you come into the lab I'll show you how to use those. Okay, when you're reaming the holes, A, check with us first to make sure that you're reaming the correct holes, and B, make sure that you're doing it along the actual axis. Sometimes, we're seeing reaming like that, but that just ruins the hole. When you're putting in the bearings just for the drive shaft on the cable transmission, it's laser cut wood. It's not particularly that great for aligning bearings. So put in, first I want you to take your bearings, make your shaft, and make sure the bearings are very nice, clean slip fit with the shaft. Then you insert one bearing, then you put the shaft through that bearing and use that shaft to help guide the other bearing while you install it. That way it will A, align the bearing better, and B, even if it isn't perfectly aligned, at least your shaft's in, so you don't have to pound on it later. Okay, install the counterbalance assembly last, because otherwise it's pretty awkward. When you're almost done and you are trying to install the cable, come and get me and Rob. We have very limited supplies for this, so we'll cut you off a length and help you crimp it and install it. And then before you guys leave with your completed prototype, please let me know and I'll videotape you. Bring your lab 2 to office hours and I'll videotape that too. But I want labs 1, 2, and 3 videotaped before anyone starts the final project. Any questions? Okay, please reread this email because it will save you a lot of time. Just so you know, I do this too. Like with all my aluminum steel parts, I have a Sharpie in my pocket constantly, and I mark off which holes are for what, because I mean it's even harder to get a dowel pin out of aluminum or steel. So this is not me being like, oh, you guys are noobs, you need to, color code. I color code all of my aluminum and steel parts every day, because I am slightly dyslexic, and that helps prevent disaster.
You're colorblind.
I'm that as well. I'm just all types of fucked up. Okay. I've gotten some emails that there are problems signing up for office hours. The reason that they're restrictive right now is because we actually don't have all of the laser cut parts. So if you decide to come in and your name's not on the list, we just don't have parts for you. It's not we're trying to be mean, it's that we don't have parts yet. Hopefully, after a night of much cutting, we can allow more people in than we were previously expecting, in which case I'll send out an email. But for now, the reason it's restricted is just because we don't have parts for you. But we'll get everyone done. Don't worry. Hi, Sony. 2 quick notes from last week. From last lecture. I just wanted to go over real quick because there was a little bit of confusion and I didn't explain it particularly well. Remember we were talking about the remote center of motion, and we were talking about the SRI design that uses cables and or belts, and a couple people said, hey, can't you go 360 degrees on that? And I hesitated. I think I punted and didn't particularly respond. So you were right, but you were also sort of wrong, so I'm going to show you. Hello. Oh, yeah, sorry. So these were the 2 simple remote centers of motion. And then the one that we're talking about now is this one. This is the one that uses, this is a cable or belt. And someone said, if I flipped the base of my prototype to the other side, we could keep rotating 360. You were correct. The reason why I didn't want to talk about it that much is because I wanted to go back and think about why that's actually not possible for me. For me, I have a counterbalance on here, and it's big, and it's a chunk of steel. And basically, if this is sort of the top of your robot, and then you have this, and this is your remote center of motion, I think up here I had a big mass or something, and so as we fold that way, the mass comes down here, and then we swing up the other way. If I did 360, this thing would be going all the way around, and I had a plate up here, so I physically couldn't do that. So keep in mind, just because part of your mechanism can do 360, it doesn't mean the whole mechanism can. And anyone else know the reason why? This is sort of okay, well maybe I just won't put a counterbalance, or maybe I'll make it smaller, or maybe I won't put that plate here, but there's a more fundamental reason. Anybody know?
I think if you put the plate on one end, it kind of goes all the way to the right? So then you're going to have a weight. It's not like you had it kind of in one line, the weights?
I'm looking for something different. I said cables or belts. That's a hint.
Do you get slack at some point?
Nope.
You'll run out of cable.
I'll run out of cable. Okay, so these could be cables or belts. There's no reason to do one or the other if you're doing limited rotation. Like if you're doing, let's say we're going to go 90 and then 90 on the other way, so 180. So belts or cables would work just fine. But if you want to be able to do 360, And then, so the thing about going 360 is that tempts you to keep going, right? Like if you rotate all the way down here, and you can rotate all the way down here the other way, it's obnoxious that to go like 1 degree, you've got to spin all the way back around, right? So in my mind, if I want to be able to go 360, and I don't want the temptation of going through that inflection point without going all the way back around, I don't use something that is meant for finite rotation like a cable. You see what I'm saying? Like you could use a cable and you could do 360, or maybe you could do 720. At some point though, you're going to have to be keeping track of your wraps, and personally it just irritates the crap out of me to have what's meant to be limited rotation and the temptation of using it as continuous rotation. Does that make sense to everyone?
You can have a problem with cables, I see that, but with belts, it's different, right? Because the prototype you showed, you could keep that.
Exactly. So now we have one last issue. So let's say we do want 360. I don't like the temptation of coming all the way here and having to wrap back around, so I'm going to use a belt. Anyone know what the issue will be? What's one of the main differences between cables and belts? That's one. What's another? What's a severe performance limitation, belts versus cables? I'll give you the answer. It's backlash. So remember I told you that most of the time belts don't experience that bad of backlash unless you're really driving them hard. It turns out the way for remote centers of motion, it actually does drive the belt pretty hard because you have a lot of mass on it. You're trying to transfer a lot of torque because of these huge links over pretty small pulley diameter. So you actually will experience backlash. And because the remote center of motion actually needs to be where it is, and you have the whole S equals R d theta, you need to figure out what S is acceptable. And then you know your link length is R, and then that tells you what d theta you can tolerate for backlash. And when I did my calculations for sort of the scale of actually smaller than your Lab 3, the backlash was like very unacceptable for a medical robot that I was working on. I don't remember what it was. I think it was like 10,000ths of an inch or something. And I wanted down to 1,000th of an inch. So it was, as in I wanted to place my remote center of motion within 1,000th of where it was supposed to be. And it would have been 10,000ths with the backlash. So I actually couldn't have used a belt. So to give a more general thing, belts, backlash you normally don't see unless you're overdriving them. In this case we are actually driving them pretty hard, mainly because we want this to be slender and elegant, so we have small little pulleys. So we're transmitting pretty large loads, but it's over small pulleys. So we have pretty high torques, we're experiencing the backlash. If we were doing like a wheel on a scooter, we wouldn't matter at all. I mean, the backlash would be lost in the noise. But for something, if you're doing a remote center of motion for precision, like for a medical robot, that backlash will actually kill your application. So, let's back up for a second. You guys are correct. You can in fact use a belt to go 360 on this. Just keep in mind, if you use a belt, the backlash might hurt you for some applications. And don't get tempted to use a cable because you have wrap-around issues. Okay. So that was one note. And then the next note, is that clear to everybody? Okay. The next note is we were talking about counterbalances. And between the two lectures, I forgot to mention something that I think is fairly important. You get a darker color. Okay. So say we want to counterbalance something linear. So this is our big mass. And let's put a cable over like this. Sorry. Okay. And let's put another mass here. Okay? So mass, mass. So this is counterbalanced, right? Right? Say the steel cable is negligible, most of the time it is. Say this is like, I don't know, 5 kilograms. That's really heavy. So we're not going to feel any of that steel cable. Is this counterbalanced? Yes, this is counterbalanced. Okay. Now this is a robot arm. Okay. and I got motors on it, and say I make it so it can really accelerate rapidly. Say it can accelerate rapidly at 2G. So what's going to happen? So this one, all this one's relying on is gravity. So that's 1G. And this one's going to accelerate up at 2G just because I have geared my motors because I want to really be able to whale on that thing. So what's going to happen? This goes slack and then comes off the cable, and then the whole thing falls down. So how can we solve this? Let's try again. Let's do one at a time, and I'm also going deaf, so louder and in single file.
I mean, anytime you accelerate something up, it goes slack, right?
Any other answers?
Add a second loop.
Add a second loop. Booyah. There we go, and we're done. So this starts pulling this. And then you tension these so that any change in tension won't actually lose tension. Uh-huh.
I still haven't understood why you would want to use counterbalancing at all versus, let's say, some sort of like weight mechanism or.
Okay, so say this is connected rigidly to a knife, and this is my hand. It's basically my robot. And when the power goes off, we don't want it to move, right? We don't want it to fall into me. If we did a brake where when the power goes off, it breaks, well, I still want to move this away from my hand, right? So I can remove my hand safely. That means someone has to go over to the brake and manually pull the brake out and then lift up while I pull out my hand.
When you would have a ratchet on brake or something, it just allows one motion.
Have you tried to order those?
What?
Tried to order those. So I mean, your idea of putting a brake on this is fine, except for the fact that the question is, can you buy that brake? Can you buy the brake? Can you install it on the motor? Can you get one that's ratcheting? Can you get one that's, when the power is off, it latches, but then you can get away easily? The answer is you can't really. I tried. You can't really buy brakes that behave the way you would want for safety like this. So you don't really have much of an option. And even if you could buy one, I would argue it's still a pain in the butt, because you don't want when the robot goes down to have to call on a team of people to come over to extract the patient. You want the operator of the robot with his or her two hands to be able to just pull this up and help the patient out. So if you have to go back somewhere inside the mechanism and undo a ratchet or undo a brake, that's extra time and extra dexterity required when I could just counterbalance it. I mean, we could make plenty of arguments. Another reason is if this is counterbalanced, I can use a smaller motor. So, I mean, I'll have inertia issues in terms of I can't spin the motor up really quickly for the angular acceleration. But if it's counterbalanced and it's just staying there, my motor isn't burning power. If it's not counterbalanced, then my motor is constantly trying to fight gravity. And so if it's constantly trying to fight gravity, we need a bigger motor. And then if we have a bigger motor, that means the converse is that at some point that bigger motor might try to pile drive this into the person's hand. So imagine this. Imagine we spec our motor so it can only ever apply one force downwards, right? If it's not counterbalanced, then we need a stronger motor. Now say the stronger motor decides to flip that direction, and say it weighs 9 pounds. So now we have a max of 10 pounds that we're able to pile drive down on the person's hand. So like with the PR2, the reason why they went with counterbalancing is they wanted weak motors that weren't capable of smacking someone's head off. So to use a weak motor for safety, then they need to counterbalance everything so the weak motor could actually drive the links.
But I would counterbalancing because you could just use a brake to sort of brake and you can not moving.
Let's argue about this outside of class. I think that would be better. Okay, does everybody get at least mathematically why we're putting this second loop, whether that's a good idea or not? So let's talk about servos. So servo motors are for finite rotation. Let me go ahead and show you what they look like. Okay. So this is a servo motor down here, these little things, and probably most of you recognize them. You see these all over the place on little RC helicopters and cars and planes. And so this black part is made out of plastic, and it contains a motor, a gear train, and a potentiometer. This white part is called the servo horn, like a rhinoceros horn, and that's what you actually will bolt the rest of your robot to. And so they sell a variety of servo horns. So we have round ones, we have the sort of the cross pattern. This one's kind of cool. This you can slide in and out by loosening the screw, so you can actually change the lever arm depending on how your mechanism is working. You'll notice they're boxy, so they're meant to be rectangular. So let me show you what a dissected one looks like. So this is the black thing in this case is a servo horn, and we turn it over and we see a gear train in here, and then deep inside it on the other half, so this is the bottom half, and I've taken this out. So a little circuit board, there's a DC motor with a gear on it. Let me zoom in. Okay, and then what's the black thing? Black thing's a potentiometer. Okay, so let's go back to the gear train. So notice how there's a central gear and then there are gears left and right. And see how the one on your right has a slot in it? And let's go back and look at this potentiometer. Can you see that that is slot? Kind of hard. So that slot goes in the slotted gear. So basically the way this works is we've got a control wire here. Can everyone see the colors? The colors are red, black, and white. So what's black? What's red? And what's white? Signal. Okay. So we come in with red, with power, ground, and signal. Come into our little speed controller circuit board. We spin this motor. The motor goes into this gearbox. This is the output shaft here. One of them, I guess, here, and then the others for the potentiometer. So the potentiometer is just keeping track of where we are. So the reason we use servos is they are very compact closed loop controllers. So it's not like you send a voltage and then you read an encoder. You simply tell it, go to this position, and it goes to that position. Now let's look at something else. Remember how I told you with nice metal Maxon motors you could clamp on the outside? Don't do this to servos. Servos are almost always plastic. If you clamp on the outside, you'll just crush the gears. The clearance is very tight between the gears and the circuit board and the casing. So don't clamp on them. How do you think we might attach to a servo? These little holes here. And just to show you, the only thing holding this whole thing together, those 4 long screws, that's it. Okay, so you see these bolt holes here? So when you order a servo, they come like this in terms of there's nothing in the holes, okay? Now what about these? What have I done here? The black things are called grommets. They're rubber. And then those little copper things, I'm not sure what they're called, but they go inside of the grommets. And basically that gives you a little bit of vibration isolation between the mechanism and the servo. Now, I don't think you need these unless you're doing like an RC plane or helicopter or car that's really going to be shaking the hell out of your motor. But, I mean, these are mainly meant for little hobby vehicles, so that's why they do this. Okay, so let's look at the servo horn. Get a screwdriver. So these servo horns are removable. So to replace the servo horn, we have a single screw here, and then this horn just pops off. Okay? So now we're left with this. We can make our own servo horns, and in fact I will tell you about that in a sec. So there's just a single screw that holds that on. Now, someone tell me what they think might be how you actually transfer torque, because the screw is not for transferring torque, that's just for keeping it on there. Yes, the head of the servo has teeth. Do you know what the teeth are called? They're called the spline. S-P-L-I-N-E. There they are in the microscope. Do those look like normal gear teeth? Do they look like normal belt teeth? No. I'm not sure how they come up with these things, but when you buy a servo, they're sort of a whatever that particular manufacturer and that particular servo decided to make them. So this is what the spline looks like, and those little notches allow us to transfer torque. Now, because this is plastic, what they've done is basically you're sort of doing a light press fit between the servo horn and the spline, and plastic is really good about it. You can do a light press fit so there's no wiggle and then take it off easily. So let's zoom in on the servo horn just so I can show you what that looks like.
Do you know what kind of plastic it is?
No, I don't. Okay, so this is what the servo horn looks like. So you can see matching teeth. Now, someone tell me something obvious. Huh? One the same? Okay. Does that spline pattern go all the way through? No, why not? Exactly. So, if this is the spline on our motor, if we had that spline go all the way through, then we could take it and go this way. And so this is the black plastic, and this is the spline. And then what would happen is, if our spline went all the way down, then we would rub here, and that's not a bearing surface, so we'd have friction and it would seize up. So instead what they do, if that's the spline, they make it let me make this more obvious from the okay, so now we have this clearance here. And so when we bolt, we're bolting this little flange here against the face of the spline. And that's, does everyone see that? So that single screw sits on top of whatever the servo horn is, and we touch here at this interface. So that positions us axially against the bottom of this hole, but we still have gap to rotate without creating friction. So, say we wanted to make our own servo spline. What do you guys think is the first step for making your own servo spline? What would be a more precise way than taking a picture of it?
Get the CAD from the manufacturer.
Get the CAD from the manufacturer. There is no way around this. If you don't have the CAD from the manufacturer, don't even try. It'll just destroy your motor. I have never had a case of the manufacturer refusing to give it to me, and I asked for it this afternoon and they gave it to me within the hour. So this is what they'll send you.
You can either go for like the really cheapo hobby shop ones where you can't really track down the manufacturer.
I've never seen a servo that doesn't have the manufacturer stamped on it. They're proud of it. They every time you go to an airfield and you see somebody's airplane and you like it, you go over. They want you to know it's high-tech or Futaba or what have you. So I've never seen an unlabeled one. And if it is unlabeled, you shouldn't use it. You should go find one that is labeled. So these are the very detailed dimensions of the spline. And this right here is what we really need. This is the tooth pattern. Okay? So based on that, this afternoon, I made a little part. So this is the spline pattern. It took about a minute and a half to make this. It's very simple. And then the fruits of my labor. Just going to show you what it looks like. Okay. See that? It's at an angle, so it's a little not real pretty. That's just the laser cut version. It's a little, the edges look rounded because I'm having trouble focusing it, but this works great. So let's try it out. So,
Another question.
uh-huh.
So, is there a certain like amount of torque that the hub can handle?
Yes.
What, like, if you by chance overload it with your own?
Yeah, then it'll just rip all the teeth off.
So how do you know how much is?
The manufacturer will tell you. So when you look up and it says torque specifications, I think they mean if you override this, it'll rip all the teeth of the gear out. And that, it really will. I've ripped a lot of servos in half. We'll talk about that in a sec. Okay. So, if I was going to make this, do you think that single part would suffice? It would slip down. So we're going to laminate. So what we're going to do is this plate has a hole for the screw, and then the plate below has what? A hole for the spline. So this is for the spline. By the way, you're doing this for the final project, so now I see more pins. Screw hole. Okay, so your screw is here, and it comes down, and then your spline from the motor is here. Okay, now does this look good? Looks good to me. Basically, we just laser cut something to replicate this little flange. So this flange here is what helps seat our assembly so that we still have a gap here, a clearance, so we can rotate. And then the spline here is what transfers torque. And then you're going to put dowel pins and screws between here, the dowel pins to align, and the screw ones to keep them from coming apart. So let me show you what this actually looks like in the laser cut one that I did.
But how is the screw attached to his spline?
We're just putting it through the hole. Okay, so let me focus. Okay, so this is what the laser cut assembly looks like. The central hole is for the screw that screws into this spline. At the bottom of that hole is what locates the assembly against the face of the spline. And then the spline is the teeth of the spline are what's actually transferring torque from the servo spline. Okay, any questions about this?
Well, I guess I've sort of taken this for granted from previous labs, but when you're laser cutting a gear, do you have to set it like any special settings, or will it just work like straight?
Yeah, no. Remember the whole, if this is a circle, if we cut on the circle, will it be the right diameter? No, because we have some finite width to the laser beam. So what you do is you actually set it in so that when you move this, it's basically the nominal diameter plus the laser diameter.
So you took the specs that the manufacturer gave you and then offset it.
Exactly. But you guys don't have to worry about that. I have to worry about that. It's actually pretty easy. Well, it's annoying, but it's easy. So every time you guys send me a part, then I go ahead and set the offset so that I actually give you the true dimensions you were expecting.
So if you're not traveling, to worry about that.
Nope. Except for what? What's the one time you guys have been worrying about it? For the little circular holes. So the thing is, in your parts, you have like a billion little screw and dowel holes. If I had to click every one of those, I'd lose my mind. But there's only like one spline and one notch and one outside for most parts. So I'm happy to click those. And the thing is, most of the holes in CAD are just for concentricity. You're not looking to see if the edge meets something else. Whereas the non-holes, you're always looking for, do the edges line up, et cetera, which is why I want the true dimensions in CAD. So let's take this and put it on my servo. And Ellis, can you give me a hand, please, with the camera? Okay, here you go. Okay. So here's the motor. Now I just made this whatever to show you that I can literally laser cut arbitrary shapes now for my servo horn. Press it on. Insert my single screw. Don't over tighten these. Use a little, see how, can you zoom out for a sec? See how skinny this screwdriver is? Use a skinny screwdriver to keep you from stripping out the plastic. Tighten it. Well, it's on. Okay, so keep that on that. And I suppose we'll watch it move now. Is that one moving? Cool. Okay. Now, does this look like a whole lot of rotation? No? Typically with little, now it varies from servo motor to servo motor, but typically you get 180 degrees of rotation. Maybe it'll be 30 less, maybe it'll be 30 more. You never get 360 unless they're super nice. And I can set different things. I can set the velocity, so watch this. I guess I should set it at non-zero. So that's pretty slow, right? Versus really fast. Okay? And I can set the acceleration, I can set the min position and the max position as long as it's within the roughly 180. Okay, I think... Now, one last thing. Say I didn't put this in the right angle. Say on my computer, I'm going to come over and say I want you to go mid-range, okay? So right now it's exactly halfway in the workspace. And say I want this rod to be parallel to the body of my motor. Is it parallel right now? Okay. Any suggestions for how I might fix that?
Take it off.
Take it off. Put it back on. Rescrew. Any problems with this? So that's about as close as I can get. It's kind of hard to see. That's not perfectly parallel. Anyone know why it's not perfectly parallel? Because the spline. So whatever the angle is between the spline teeth, that's the resolution you're going to be able to get in terms of putting stuff on precisely. So don't think, oh, I'm gonna put my servo horn on within like 1 degree. It's not going to happen. You're going to get like 15 degrees. Now what we could do is we could put some type of slotting mechanism on this top plate that allows us to rotate the top plate and then bolt it down to the bottom plate. That would be fine. Then we could get much more precise. But just keep in mind, if all you're going to do is rely on taking it off and putting it back on, you've got the resolution of the spline teeth increment.
So how did you control the speed? Did you set a series of pulses at a different rate?
Let's talk about that now. We're good, Ellis. Thanks. So now that we know how the servos are built, let's take a look. Okay. PWM. Everybody remember that? That's what drives servos. So you have a high pulse, a low pulse, high pulse, low pulse. This is your drive frequency period, which is 1 over the frequency. And then this is your duty cycle, or in terms of time, this is the pulse width. Okay. Now remember, before we said we could go from 0% duty cycle to 100% duty cycle. Do you think that would work in this case? No. The PWM for DC motors is very different from the PWM for servos. Please don't mix and match them. They won't work and they will fry. So again, this is manufacturer specific. To know what pulse width to set up, you have to actually check that servo and what it's looking for. I mean, they're pretty much standardized at this point, but there are some outliers. So let's take a look at this picture. This is about as accurate as you could expect from Wikipedia, so don't quote me on this. But a pretty common time in between pulses is 20 milliseconds. And then this is actually pretty common too. This pulse width is 1500 microseconds, so 1.5 millisecond, 2 millisecond, and then 1 millisecond. Okay? And you'll notice the difference of half a millisecond is the difference between minus 90 and plus 90. Sorry, minus 90 and central, and then central and plus 90. What else does this tell you? Somebody tell me about 20 milliseconds. What does that limit? It limits how fast I'm going to be able to update and send commands to the motor. So don't try to give it commands every millisecond thinking you're going to do a kilohertz, because it literally can't understand that protocol. Do you know what happens when you send a servo the wrong protocol? It doesn't move. Maybe it smokes. Typically, do you think this would be fun to program? And let's direct this to the 218ers. This is not fun to program these pulse widths. You have to use all types of output comparers, or hopefully you'll have a PWM library. But I mean, you can do it, and it's good experience. But once you know how to do it, if you can, you buy a plug-and-play servo controller. Particularly because most of the time people use servos, they have like a lot of them, and you don't have enough output comparers and PWM outputs on most microcontrollers for that many servos. So instead, you buy one of the 20,000 different servo driver boards that exist out there. For the final project, you guys will use fidgets, and that's what I use to drive this. So I think for like 90 bucks, I got 4 servos and a plug-and-play USB controller. And it abstracts it. So now I got a C API, and I send it commands like go to position, and it does it. And I don't have to worry about the communication protocol or anything. And to show you why this matters, let's come in here. Okay, so one of the nice things about fidgets is all you have to do is plug in power, plug in the USB, double click on fidgets, double click on the servo controller, and this pops up. So now I choose my servo, I engage it, and I can hear that noise. That's the servo moving, and I can set the velocity, acceleration, max position, min position, and I don't have to touch any of the pulse width. Now say I have a different motor. Maybe it has different position limits and different slew rates. This drop-down menu, this tells me all the different servos that it already knows how to use. And for those of you who are familiar with some of these, you'll recognize some of these. Forgelli's are really nice little servo linear actuators we'll go over another week. So let's talk about something else. How about this one? Hitech_HS645MG. Okay? And how about this one? This is the one we're using right now, Hitech HS422. Now, don't worry about slew rates and torque and all of that. I'm worried about materials. Tell me what the difference between this servo, the HS422, and this servo, the HS645MG is. What's that MG for? Metal gears. This means that the gear train is made out of metal instead of plastic. And so it's way harder to rip the teeth off of the metal gears than it is the plastic ones. So if you need a high torque servo, you probably want a metal gear servo, and there's likely to be MG somewhere in the part number. They take these things seriously. The specs do mean if you go at that torque specification, it will start to rip things. So make sure that you get metal gears if you need them. Okay.
Is that measuring the position of the servo on the control line?
Huh?
Your fidgets thing is not the actual position of the servo.
Uh-huh.
How does it know that? If there's
It can also query it, I think. I'm not sure how they do all their drivers. Ah, yes, that's why. So on their board, we'll get to that in a sec. In fact, let's get to that right now. There are two main ways to control servos. Well, these are hobby servos, okay? The ones with the little cheap ones with the plastic horns, those are hobby servos. So I'm sure you guys recognize these. So this is like the type of servo controller that you'd use for a helicopter or plane or car, and so you turn it on and it'll have a bunch of different things. I hate these because then you need a receiver and then you need a NiCad battery pack or hopefully LiPo. It's just a pain. The batteries seem jinxed. Also, how do I hook this up to my computer? I mean, all the robots I build are computer controlled, so that's sort of a pain in the butt. So that is one way. That's like the old school way, or the Hollywood way. And I'll show you why I mean Hollywood in a second. And then the sort of, you guys as robotics researchers, you're going to be doing it with a board like Fidget's where it plugs in on USB. So the difference is, do you think you can query the position on this? Do you think this is going to have like a live output of where your servo is? No. You tell it, I want you to go to X degrees, it goes to X degrees, and it doesn't say anything about where it actually is. The Fidgets on their own board have custom commands where you can also ask it where it is. So what's cool is you can do things like if this is time and this is theta, and you command it to go like this, then in a different color, I'm going to put these permanent markers over here because I will draw on the board with them eventually. Then you tell it go here, and then you query, and then you can plot the other curve, and you can see that it's trying to get there, but it's not there yet. Everybody get what I'm saying? Okay. So you saw so we told you that these are used a lot in RC helicopters and I didn't tell you that. Planes and cars. They also use these a lot in animatronics. And rather than explaining it, I'm just going to show you what I mean. I think this is awesome, so I'm going to take up valuable class time to show you a movie. John Nolan is a special effects guy. He's awesome. All of this is servos. And it gets freakier and freakier. So he's vacuum forming a little mask for it. So a lot of the funny ads on TV and the weird sci-fi movies that I love have a lot of animatronics, and they all rely on servos. This one's awesome. So notice all these movements are from finite rotations. You don't see any wheels that keep turning endlessly. Now, despite all of this, these guys are still using these old school RC and RF-based radio controllers. And it's kind of like a piano player where their fingers get very accustomed to the motions of the radios. But my dream is one day to do this, but have the computer controlling over the motions with some type of motion capture.
Oh, you mean that it's not pre-recorded, the guy actually goes...
No, it's not pre-recorded. Yeah. So the issue is if you're shooting a movie and you want, okay, let's do that scene again, then, you know, the set, and it's like, there could be up to like 10 or 12 people for like an animatronic face, because you only have maybe 2 servos under your control at one time. Then you have teams of these people, and they can't recreate it the same way every time. It's literally a performance. That's why they give, you know, Oscars for stuff like this, is because it's not a computer doing it, it's actual men and women doing it. Yep.
But don't you think this is recently getting replaced with like animation and stuff like that, with special effects?
I mean, that's a big question for me. I'm not sure. For some reason, they keep doing it. I mean, some of the areas that you can't replace this. If you go to like Disney World and you see some of their puppets, you can't do special effects on people's eyeballs in terms of 3D animation. So you actually do need puppets that are capable of doing this if people are in the room.
Why use servos and not separate motors?
The servos have closed loop control. So if a stepper slips, then you're lost. You don't know where you are. But you can't slip a servo and get lost.
But steppers, there's a region where they're spec not to slip.
But how do you know if you're within that region? The issue is you spec your robot for one load and someone kicks it and then it slips and then you're screwed. Also, servos, for the torque they output, are ridiculously small. I mean, just ridiculously small. I'll show you one in a sec. I can't believe that you get that much torque from such a tiny little package. It's because they're heavily geared. So, if at this point any of you want to switch your final project to a robotic squirrel, the answer is no. I don't want that on my history.
So would you only use a stepper if you wanted position control and the ability to rotate continuously?
Yeah. It's a tree. So do you guys know what mechanisms they're using in here? Actually, let's go back a sec. Okay. So what mechanism is this? Push-pull rod, a rigid linkage. And what about this? I know it's kind of hard to see. It's curved. It's a push-pull cable in a sheath. So, I mean, there are lots of ways to use servos, but the two standard ones are either rigid linkage, so it's a push-pull rod, or like the bike cable in a sheath. And a lot of these geometries are pretty crazy, and they need flexibility. So the push-pull cable in a sheath is heavily used. So there you have it. Okay, so some of you might hear of something called a digital servo as opposed to an analog servo. Does anyone know what the difference is?
Is it encoder-based rather than control?
As far as I can tell, the only difference is that the digital servos, you can program their parameters, like the stiffness of the PID loop, whereas the analog ones you don't. So by analog, I mean you plug it in and the RF communication comes in and it goes to the position. And I'm not sure if any of them are programmable. I don't think so. Maybe you can, some special. You probably have to tweak little knobs somewhere. The digital ones you plug into your computer and it popped up and you set the gains for the PID loop. And if you're doing really high performance stuff, that can be very important. You still control it with the same type of PWM signal. So it's not digital in the sense of you don't send it like a serial command that says go here. You still send it that same PWM pulse, but you can program the PID. Yep.
So since you're mentioning PID, what's the advantages or disadvantages of a DC brush motor with PID versus a servo? Or are they the same?
It's the same thing, but these are tiny and they are already assembled and they work. So the DC motor, if you wanted to build this from scratch, you'd need a DC motor and a gear head and an encoder and then a communication protocol and a motor controller. And that's really expensive and bulky. These you buy for $30 and you're done. You bolt them in and you're good to go. So it's just a black box solution.
So there's no difference in like torques or like,
Torques?
Yeah.
Oh, of course there are. I mean, you don't just pick up any servo and assume it will work because it's a servo. You have to make sure. Well, what do you think would be important for specifications in terms of a servo motor? Okay, I heard torque. What else? Speed? Huh?
Angle.
The angle, what else? Size / geometry. So all of these things matter. And so like I said, it's not one shoe fits all, but you have to make sure you've got sufficient torque and speed and angle and size. So a lot of the high torque ones are slow as hell. So they wouldn't be good for animatronics because you have the little duck trying to quack and it's quacking like this. So it's a trade-off between these. Now let's look at size for a second, and you'll understand what I mean. Okay, so I'm just going to hold this in my hand so you can see how big it is. It's a pretty standard little hobby motor. It's not that big. They get a lot bigger. And then let me put the quarter next to it so you can see the quarter. So that's about the width of a quarter. Now I'm going to take, this is called the Bluebird Ultra Micro Servo. Now look at that. It's smaller than a quarter. So if you didn't have high loads, I don't know, maybe you want to bat the animatronic eyelashes, then maybe you'll go with a tiny little ultra micro. They're called ultra micro servos. So if you wanted to build this from scratch, I don't know of any encoders or potentiometers that are that small. I don't even know where to start to order them. I also don't know where to order motors that small or gears that small, and I sure as hell don't want to assemble them all. So I think this was like $30, and you literally can't build it yourself without like a week of research and trial and error. Okay, let's see what else we got about servos. So we talked about we could drive these with push-pull rods or the cable sheath, like the bike cable. You can also bolt directly to the servo horn. These standard servo horns you can't actually. See these little holes? They're really tiny. And there isn't particularly a lot of clearance. So you could put, I've seen a lot of people drill out those holes to fit like an M2 screw and then they'll put a nut on the other side. But how are you going to tighten that nut? You're going to put a pair of pliers in there? It's a pain in the butt. So whenever I use a servo for research, I just custom laser cut my own servo horn, and then I can self-tap into the wood, and it's a lot easier to connect directly to it. So for your guys' final projects, I would recommend not using any of the standard servo horns and just laser cutting your own.
What do you have against acrylic again?
It's brittle. So if you put a bearing into acrylic, it might be fine for a day or two, but at some point it will crack in half. Also, it smells terrible. Like really bad. Like death bad. So let's see. Somebody, how do you think, actually I can show you, I can answer that. Okay, this is the inside of one. This gear right here is what connects to the output right here. You think you got room in there for 2 ball bearings? No. There's 1 plastic bushing. Let's draw that. Remember how many bearings we've been using on all of our contraptions? 2. And why is that? To limit the movement, but also because it supports way higher torques. Remember, if we have a shaft, and then we have 1 bearing here, and then we twist the shaft, then that's going to crush the race here. We put a second bearing, now we can resist that with a force here and a force here. And so the radial forces are a lot lower. We don't have room for this on servos because they're tiny. So instead they have 1, and let's put balls here so we can see those are ball bearings. We have 1 single bushing. So the bushing, so this is the shaft that comes up, and this is the servo horn, and then this is our gear here. So you get more play that way, and you also don't have a very big separation between the contact points here and here. There are no balls, which means that the moment loads that this can support and the radial loads that this can support are really low compared to if you had like a gearbox with 2 ball bearings. So what do you think this means practically about how we attach and what we attach to our servo? It needs to be supported. So if you're not going to support that servo horn with another bearing somewhere, then would you want to use a belt?
Right on the servo.
No, do not put belts directly on the servo horn. They're good for gears. You can do gears. I wouldn't do a friction drive. That'll kill it too. I wouldn't hang any weights off of it. And if you're going to have to support the other end, you probably don't want to end up using a hobby servo because it sort of defeats the purpose, right? Like plug and play, and then we build a structure to plug it in. It defeats the purpose of plug and play.
Can you do a counterbalance on it?
The overall weight of that counterbalance will also kill the bushing. My rule is if you take a simple part and to use it have a very complicated infrastructure, it's defeated the purpose. But we do have an alternative, which is, anyone heard of Robotis? Anyone heard of Dynamixel? Hey, no one's heard of this. This is exciting. Okay, let me show it to you. So there's these are the hobby servos. These are dudes in their 40s on the weekends flying planes. And then the next step up is these are called Dynamixels, and these are actually used in a lot of robotics research. And right now at ICRA as we speak, Robotis has a booth there selling these by the billions. They're Korean, so it's a little beefier in terms of size. This is
Sorry, how do you spell that?
Robot. IS. Dyna, D-Y-N-A, Mixel, M-I-X-E-L. And they sell them everywhere. The cheap ones are the AX-12s. Okay, so let's look at this. This is the servo horn. And it's a little hard to see. Do you see the glint of metal in the servo horn? Those are M2 nuts that are embedded. So you bolt directly to the servo horn. So that's cool. We don't actually have to custom mod the servo horn. Do you see the thing in the center? See the little ridge in the center of the servo horn? Anybody? What's that used for? Location. So right out of the box, we have a central hub for locating laser cut parts, and we have tapped a hole pattern of 4 tapped for M2 holes, so we can bolt directly to it. Someone tell me. So they sell these as little attachments. So someone tell me something obvious about this. It attaches on both sides. So with our hobby servos, we only had access to the shaft on one side, and so the loads were pretty low. On the Robotis Dynamixels, we have access to both sides. Now it's still bushings, so we need to keep in mind these aren't ball bearings. It's bushings, but at least we have it on both sides, so that increases our torque and radial capacity load capacities a lot. Okay, now to attach these, they have these little adapter plates with hole patterns. And then there are hole patterns here. These are meant to be plug and play for high loads in actual research and products. And they're modular because they got screw holes everywhere. See? Some of those are tapped. Some of them are just through holes. And I'm using these on my dissertation robot, and they're super awesome. Huge. So let me go to the website. Okay, so they have a whole line, starting with wee little men here, the AX12s, all the way up to the MX series. And basically, I think the AX12s start around $200. I don't even know how much the MX ones are. I can't afford them, but they're nice. So the AX12s are good enough that people were doing research with them, and the MXs, the MX series characteristics, you can actually do current-based torque control. So it's a servo that's not just doing position control, it's doing torque control based on actual currents. Below the MX series is just position-based. But these you plug into your USB and you give it commands, and it has a whole slew of different nice commands you can give it to set acceleration and velocity and limits. They can go a full 360 with position control, so anywhere from 0 to 360. And then in velocity control, they can rotate continuously. Can you do that with a hobby servo? Why not? the potentiometer. So all the hobby servos have little potentiometers in them, and potentiometers are for finite rotation only. So hobby servos, unless you take it apart and take out the potentiometer and resolder something else in there, can't do continuous rotation. They're uncommon. So Ellis is correct. You can buy them. They're uncommon. Most of the hobby servos you get are going to be finite rotation. If you do need continuous rotation, I'd probably go with these. They're just a lot nicer to deal with, unless you don't have the money, in which case get the contact from Ellis.
There's some site that has these AX12s for only $45.
$45.
I don't know if it's right.
Is it a .net? Is it a .cn? I've never bought them for under a couple hundred. That's awesome if that's the case, but I wouldn't be surprised if those are hot motors. So inside I'm not sure what's inside the AX12, but some of the nicer ones, guess what type of DC motor is driving it? What's the only other DC motor I've told you about? Nope, like the manufacturer. Maxons. So part of the reason these things are expensive is because Maxons are expensive, and these are built out of, some of these are built out of Maxons. And I would bet my eye teeth that it's the torque control ones. So this is nice because you're getting torque control, and you don't have to buy the Maxon or the Copley amps or deal with the inductors. You send it a digital command, and it does torque control at the joint, and it's compact. And
Are they back driving?
it depends on the gearing. If it's high gearing, no. And if it isn't, then yeah, they are back drivable. Some of them, like the ones I've got, are back drivable.
So you don't need a control board at all? You plug it directly into USB?
Almost. So let's talk about that. So you plug them into your USB, but not as a USB device. They're half duplex TTL UART. The 218ers will know UART is a serial protocol, and they have serial to USB converters. For Linux, it's actually built into the kernel. So what you do is you get a serial to USB converter cord, and it's like a 2 resistor circuit. So you put that. So you get the cord here. Let's draw it out. If you want to use a Dynamixel, now they because of their popularity, they've been improving a lot lately, and I haven't bought them within the last 2 years. I've been using them for 2 years, but I haven't bought any new for 2 years. So hopefully they've solved this. So this is your USB, and this is your UART, and then you need a little circuit to actually connect that to your Dynamixel. And this is just like pull-up resistors. And then here, this uses an FTDI serial to USB chip. And then on your computer, it just comes up as TTY. What's the serial? One last time? S0, something like that. TTY something in Linux, or Windows it'll be COM0. So basically, after you do all of this, you plug it in on Windows. It comes up as COM0 or COM1 or COM2, and you program it. And it's TTY something on Linux. I'm not elite enough to have that memorized. They sell these USB to serial cables on SparkFun, and then this little circuit is like 2 resistors, I think, and then you plug it into your Dynamixel. The nice thing is Dynamixels are daisy chainable, so you only need one cord to go up to like 256 of them, I think. So if you did, now you're going to have issues in terms of your USB speed, but you theoretically only need one cord to control a whole robot of these. Now there is a downside. Anyone know what I mean by half duplex communication protocol? Yeah. So you're able to send commands to the servo, and it's able to send responses to you, but you can't do them at the same time. So full duplex would be, and some of these are full duplex, I think. Like the really nice ones are full duplex, I think. Maybe not. I don't remember. I haven't bought them. But the ones I have, the AX12s, are half duplex. So you would say, hey, where are you? And then it would say, I'm here. Instead of, go here, go here, go here, and it's constantly saying, I'm here, I'm here, I'm here. So that cuts your speed in half if you're always asking it where it is. And coding these I think they've released an API recently. I coded it from scratch, so I was like sending bytes, and it was terrible. But hopefully it's gotten better. Okay, let's see. Any questions about servos?
What happens when the power turns off? Does it just keep the same position?
No, it's backdrivable if it's a low gear ratio, but it doesn't try to. Once the juice is off, it can't do anything.
And when you give it a position, does it run until it hits that position? In other words, if you were to not saying you should do this, but if you were to hold the end, would it actually keep pushing you until it reaches a position?
If you tell it to go to 90 and you hold it at 45, it will struggle with you until it gets there. That will possibly burn up your motor. I don't think most hobby servos have any type of internal temperature sensor, so they burn up really easily. The Dynamixels have an over torque and an over temperature, so if you exceed either the load capacity or the temperature, it shuts down and gives you an error flag. And you can read that digitally. Yep.
Does it slow down before it gets to the position? Like it has to accelerate, right?
Yeah. A lot of the nicer boards have built-in trajectory planners so that it doesn't get there and then cut power. It tries to do a smooth trajectory. So again, these are good for continuous. The Dynamixel is good for continuous rotation. Also, they're just beefier for higher loads. Nicer motors. One other caution about servos: they're really annoyingly loud. So you guys could all hear them. It's just there aren't even any loads on that. Anyone know why they're loud? The gears. The gears are what's noisy. Okay, let's talk about 80-20. Who knows what 80-20 is? It's this stuff. Okay. So 80-20 is modular aluminum framing. And here, I'll pass this out. I need these back at the end of the day, please. And then I'll keep these here for me. So the first thing to notice, what would be the cross section? What's the aspect ratio here? 1:1. That doesn't have to be. They have 2:1, or this is 3:1. They also have 2:1, and then this is about the small size you can get from 80-20. I think Masumi has smaller, and there are some other companies that sell really tiny stuff. And this is the big boy. I actually use this in my robot, believe it or not. So let's look at these slots. I can bolt to any of these slots. Do you think just a normal hex nut works? No. So let's zoom in on that, see what it looks like. Okay, see the shape of these nuts? These are called T-nuts. They don't really look like T's to me, but at any rate, they're called T-nuts. So they're pretty long, and they're built so that they slide into the slot, but don't come out. Okay? And there are various connectors. So Rob, can you zoom in on this giant frame I'm about to get out? So this is just a quick example. I mean, you can literally do anything you want. This is, I think they call themselves the industrial erector set. So this is just a frame out of 80-20. Well, this is actually Masumi's version of 80-20. So I have right angle connectors here and here. Now they have just about every connector you can think of. They literally have it. And if you haven't, I generally don't read manuals or product catalogs, but giving the 80-20 and the Masumi a read is actually worth it. I mean, not a read, it's like a picture book, but to let you know, they have rotary joints, they have doors for enclosures, they have little Velcro attachments so you can attach things with Velcro, they have different types of gussets, they have everything. It's pretty sweet. So let's just, mainly 80-20 is sort of self-explanatory, but let's go over this. So 80-20 is the namesake. They're a US company. And they have both inch system and metric. Please only use metric, it'll make our lives easier. Okay, Masumi has only metric. They're a direct competitor. So some of the differences are precision of cut. If you get this and you cut this yourself, it's going to suck. You can do it, but it's going to be very imprecise. If you get 80/20 to do it, I don't remember what the length tolerance is, but I wasn't particularly impressed. If you get Masumi to do it, it's good enough to actually assemble a robot with the parts that come, and it'll be fairly precise. Again, I'm sorry I don't have a number. I think it's like 0.003 of an inch. Don't quote me. Look it up. They have it. But it's good enough that you're not going to get close cutting it by hand. So I would suggest probably getting it from Masumi. You have to pay extra to get 80/20 to cut it to length, and you actually have to send them a drawing, which I hate doing. So when you get it from Masumi, you simply write in, I want it 32.9 millimeters, and they send you 32.9 millimeters plus or minus like 0.1 millimeter. So that's great. In your CAD, you need to make a CAD model of this. For one thing, you need to make sure you have all the little connectors, and there are a couple other things. This is heavy stuff. If you build an entire frame out of this, it may well be several hundred pounds. My robot frame is several hundred pounds. That's a good thing for my case. We'll talk more about that. If you make your CAD, you put in your 2.7 gram per cc, and then you actually weigh the frame before you build it. If it weighs too much, then you change something. If it doesn't weigh enough, then you add something. The point is, I don't want anyone saying, well, I just need a box, and I know the dimensions of the box, so I'll just order this. You need mass properties because this stuff gets heavy really freaking quickly. So let's talk about another difference between 80/20 and Masumi. And no, I'm not being paid by either of them.
Real quick question. For our final project, do you expect us to order from Masumi?
I'm not sure. Well, it depends on the part. Some of them are overnight. Some of them are 2 days. So we'll talk more about that. Well, I will talk at you about that over the weekend. Come on. Okay. So this is, it's something like this. This is a simplified drawing of the Masumi slot, and this is flat. And this is a cartoon version, a bad cartoon version of the 80/20. Now what's the difference? Let me draw the flat across here. I don't remember how many degrees this is, but 80/20 intentionally angles these down, and they're equal. I think it's something like 4 or 8 degrees, something small. And anyone know why they do that? There you go. So we put our little T-nut in here. Okay. Then we put our part on here, and as we tighten it, these things go from angled to flat. So it's a lock washer. So the internal force between the screw and the nut that bends this flat is what keeps that nut from vibrating loose. Okay? With Masumi, if you don't use another lock washer, it will vibrate free. And I thought, well, this probably doesn't matter. But I built an 80/20 frame, and then I built a Masumi frame. Dude, that Masumi frame vibrated free in like 2 minutes. It was ridiculous. This is a really nice feature that you get from 80/20. Now, why don't I... Everyone knows what a lock washer is, right? So the lock washer is basically a little helix. And you, on its side, this is what the side looks like. When you tighten it, it flattens. Okay, don't think, let's abstract it. It's not a lock washer, it's a Belleville washer. You put it in there and it preloads it, and then we don't come loose, okay? Why might, if all we need is a lock washer, why don't we just buy this and use a lock washer? Someone has to answer. I'm getting hoarse. Anyone?
You need a regular washer below it, right?
Yeah, okay. So now we need a lock washer and a regular washer. How many screws do you think we have in the frame? These are extra components. I don't have any extra components here. Here I have 2 extra components per screw. So I have a regular washer, and then I have a lock washer. So that's 2 components times number of screws. I never counted the number of screws in my frame, but I know it's well over 1,500. So my wife came in at 10 o'clock at night a couple months, 6 months ago, and I had to build this thing, and it's big, so I couldn't like assemble it out and leave it out. I had to assemble it out and then pallet jack it into my room. So she came at 10 o'clock, and then my friend Sonny helped me, and the three of us worked on this damn thing until 5 in the morning. So from 10 to 5, three of us with like over 1,500 screws, and this I didn't have. It was still a nightmare. I was using 80/20, so I didn't need them. I would have killed myself if I had to do this for 1,500 screws. This is why it matters. Okay? Yep.
For like the 80/20, can you CNC them so you can get a close cut? Or like,
Do you mean can you modify them?
or like you said you couldn't cut it down to as precise as you would like consume.
You can cut it precise enough. I'm not happy with it. Masumi is twice. I remember Masumi's resolution in terms of the length tolerance is twice as good as 80/20's. Now you can get, if this is our rod, I can tell 80/20 put a hole here or put a hole here, but I have to make a drawing for them to do that. With Masumi, you go to their little thingamajigger, and the drop down you select I want to add holes type A, and I put in the dimension and it's done. So it's the difference between having to actually go into SolidWorks and make a drawing and have a person interpret that drawing and probably get it wrong once or twice versus Masumi does it automatically. The other thing you can do is say you want a square. You can actually get them cut at 45, that's not 45, at 45 degrees like this. So you can do these types of joints. You don't want to cut that by hand. It's not going to work. Order that. And if it were me, I'd order it from Masumi. Just keep in mind, if you order from Masumi, you have a lot more components. So here's what I would recommend. If you don't have a lot of components, do Masumi. If there aren't that many screws, it's not going to drive you crazy. Masumi's quicker. I think in some respects they might be cheaper. They have a wider selection. If you have a lot of components, do 80/20. Okay, now say we do 80/20. What's the problem with these little angle things? No. Say I want to check if my table is level. Okay? So I put a level right here. None of these sides are square. It drives me nuts. When you get out a pair of calipers, you're like, what is this? It's like, if you don't align the calipers just right, if you don't put the level just right, if you butt one thing up to here but you butt it against the wrong part, it makes assembly and measuring a nightmare. Because none of these are square faces. And it's not like if we zoom in that it's straight and then it goes down a little bit at the end. It basically goes down the entire way. And also the CAD for 80/20, the CAD is true to life. So when you're trying to assemble mates on the 80/20, you can't use any of the faces. You have to make planes, and then it's like, okay, well, it's 80 millimeter wide, so everything's like a 40 millimeter distance. So it's really painful in CAD. So let's review. There's a lot of information. These save you the lock washers. Great. It also means assembling you have to be super careful. With Masumi, they're extremely square. Everything is measurable very nicely and assembles orthogonally and parallel very nicely. It's you know what? Build one and build the other and go with your personal preference. But there are huge differences between them. Let's talk about nuts. So, in my T-nut. Oh, also, 80/20 comes razor sharp. They don't always deburr these things. When you're handling it, make sure that you deburr it because it will cut your hand. So say this is the slot, and this is the bolt, and then this is the nut, right? Great. Say I designed my robot. I designed a table. Let me show. All right. Imagine this table is built out of 80/20, and I design it and I assemble it perfectly. I don't forget anything. But then I decide, you know what? I'd actually like to hang a camera off of it. So it's 80/20. It's modular. I'll just put a nice little. Hey, here we go. This is my table, and it's modular. I'm going to put this right here, and put some gussets on it, and I'm going to bolt it down. Cool. Well, you didn't put the nut in here, and you assembled the whole thing. So now you have to take it apart. I'm not joking. This happens every time I assemble 80-20 framing. 80-20 being general. Aluminum extrusions. Every single freaking time I forget a nut, or I forget 10 nuts. And every time I add to it, I forget it. And then you're screwed. But there's hope. These are special nuts. So, I will need a volunteer to help me. Ellis, you're close. Do you mind volunteering? Okay. And then you get the camera. Okay, don't go too far or it's gonna rip out. Okay. So Alice is gonna hold that for 1 sec. The two main issues when you're assembling aluminum framing are this, where you forget a nut and you can't put it in later, or say, here, I'll show you here. This is for putting together part of my robot, and we'll talk about this another day. This is an assembly jig. This lifts the middle part of my robot, one person on either side, and then we lift it over the middle of my robot and I assemble it while other people support it. So these holes match a bolt pattern on a big plate of my robot. Okay? But these nuts slide around. So how do you think I got these in here? Literally, they slide around. If I were to turn this sideways and I was using the simple nuts, they'd all fall out. And this happens constantly. So what's the solution? I'm going to spring load the nuts. So here's the deal. If you order 80-20 and you don't look into fasteners, you're going to hate your life because you will have gotten the standard nuts and they aren't good for anything. You can't put them in after the fact. They slide around all over the place. So there are two types of special nuts. And actually, here, can you guys hold this, please? You hold this. Okay, and you tape. Okay. So the first thing I'm going to do is we're going to try to force a normal nut in here. Okay? Why don't you tape right there? And let's come from above. Oh, can you guys move this way, please? Sorry, Ellis is constrained by the... Okay, so let's come up. Okay, does that nut look like it's going in? Let's try. Not going in. So now, the only way to put this nut in is through the end. Okay? And watch this. Whee! It's gone. I don't know where it is. It literally left the extrusion. So that's the normal nut you're going to order on your first try, and you're going to hate your life. This is a special nut. Okay? Let's try to put this one in after the fact. Look at that. Just slides right in. It's in. Everybody see that? Okay. Now let's try this one. See what that looks like? So this one rotates in. We put it in like this, and then you take something thin and you probably want to do it with like a screw. See how that rotates into place? Okay, but I can still slide these back and forth, and that's a major pain in the ass. So I have two choices. See that? That's a spring-loaded ball. So I insert it in here. Let's tilt it. Nothing happens. It's spring-loaded in there. Now I don't know why there are two different types, but there are, so I'll show you the other one. See that? It's called a leaf spring and does the exact same thing. I put it in here and it doesn't move. See? Now let's try this. That doesn't work. Alright. Ah! Yes it does. Did everyone see what I just did there? This is so important, I'm going to back up. This one you can't put in after the fact, it's too wide. This is the nut you want from Asumi, and if you email me, I'll probably give you the part number if I dig around for a while. The two things that this single nut does are A, I can put it in after the fact, and B, it doesn't move. It's spring-loaded. If you just use this nut and you always use this nut, it will cut down your assembly time by literally 3 or 4 hours per robot. I'm not joking. Okay, and I'll take this. And Alice, can you put the camera down, please? This is one of those things where people don't think like the details of making robots matter, but it's the difference between going home for dinner and not.
How much are those nuts?
I don't know. I would pay $10 a nut though. Guess what nuts I didn't have when I was doing my robot frame? Okay.
What's the name of that part?
I don't remember, something random. Masumi will also anodize your aluminum extrusions black. Remember, it matters what your robots look like. Shiny black robots are pretty cool looking, so keep that in mind. So let me show you something. Come on. Oh. I think 10% of our class has been spent with me pressing that button. Okay. So this is what my robot sits on. This is all 80/20. Okay?
Isn't your robot super heavy?
Yes. Can you make that comment in 2 minutes? The same one. Okay. What's this black thing? It's an end cap. Let me show you what my robot would look like without it. It would look ugly. And I would get crap stuck in here, and then it would rattle around. You want to buy they're real cheap. They're like 50 cents each. These are the end caps. They're just nice plastic caps, and they make your robot look nice. They keep stuff from getting inside, and also they keep you from slitting your wrist on the razor sharp edges of the 80/20. These are really freaking sharp. They don't deburr them all. This will help you. The act of pushing this in will deburr most of it, and it'll protect you from the rest.
Maybe this whole thing is built at 80/20?
Yeah, except for this part. That part, this part was machined. Tell me about these feet. If I didn't have feet, how would my robot sit level on the ground? It wouldn't. You don't want to rely on the straightness of the 80/20 to align with the straightness or lack thereof of the floor. Clarkson floors are very bent, and less so the 80/20, but the 80/20 is still bent somewhat too. You need feet. So this is a special foot. Let me open this part for you. So this is a little ball end joint. Remember we talked about those the other day? So the way this works, this right here is threaded, and then this is a ball end joint. So if I come in here, this little thing, this is rubber. That's what actually contacts the floor. And then I can change the angle of this foot to whatever the angle between the robot and the floor needs to be. So now I can put a straight robot on a bent floor. Why is this threaded though?
Just the height.
I can adjust the height and the level. You have 4 legs on my table. That's over constrained. Okay? If I put 4 legs on a floor, the odds are something's going to wobble. So by making it threaded, and this is called a lock nut, what I do is I have a pallet jack underneath my frame, and I put it, when I go to a new spot of floor, I set the robot down and I see which way it wobbles. Then I pallet jack it up, and it takes like 5 seconds to do that. I go underneath, I adjust the little feet, then I put it back down, and it's perfect. If you don't have adjustable feet on your robot, it's going to wobble. And if your robot wobbles, your data is going to be corrupted, most likely. Okay, and so these little feet just slide into the bottom of my robot on the 80/20. I can put them wherever I want. I lock them down this way, and then I can adjust both the angle and the offset. Why do I want a big heavy robot? Okay, let me stop you. I'm going to get some similar argument if I go down this line. Let me rephrase it. You want a big, heavy robot if you're doing PhD research. If you're going to graduate and go make products, you don't want a big, heavy robot. If you're going to stay here and get a dissertation, you want a big, heavy robot. The reason being that you want the robot to be in the same position and orientation every time. You don't want... that makes me nervous. Let's try this one. Jesus Christ. Wow, that was terrible. Say I decided to put my robot on this. Everyone see that wiggle? Rob, can you get the wiggle? Okay. And then, see that? Okay, if you put a robot on this, and say your robot is doing a sinusoidal motion back and forth, and say you have accelerometers on it, then all of your data is corrupted. And eventually, it's going to wiggle and it's going to fall off, or it's going to wiggle some of the screws in the feet loose and they're going to fall off. And I have built robots on things like this, and half the time I was programming to get rid of the errors from that wiggle. Actually, the robot I did for, you remember the one that drew on a ball for experimental robotics? I spent 2 days trying to get that damn thing to work, only because I was on a really wobbly desk and there was this piece of sheet metal that they had bolted to it for some reason to make it stiffer, and it was hitting resonance with my servo loop. It was going, and it's like, wow, that's crazy. And I was really having trouble getting my robot to like chill out and do what I wanted. So what I did was I took 2 pieces of steel cable, really thick steel cable, and put it on the legs, and then tensioned the crap out of it until it was like, barely audible in terms of a guitar string, and it all went away. That's terrible. Don't do that. Don't put it on tables that can't support your robot and they wiggle. There's no point. Robots are hard enough. Why put it on a shitty table? Just get a table that makes sense. Okay, now say you have a good table, it's stiff, but it's lightweight. Like those card playing tables. So my motors produce forces, and I have moving masses in my robot. Okay? Newton, F equals ma. Okay? So A is F over m. F is set by my motors. I'm going to, produce some torque, so I'm going to have to apply forces when I decelerate my masses. And I want little a. I don't want my things wobbling around and moving. So for a given force, how do I crank down A? I crank up M. So if I have a stiff table and then I add a crap load of mass to it, it's not going to move regardless of what my robot does. So my robot, I can literally sit on top of it and it will move me around in X, Y, Z. And I'm not joking. It can lift me in X, Y, and Z. And I think my 80-20 frame with the top is 500 pounds. Awesome. It literally doesn't move. I've never seen it wobble or move ever, no matter what. I've literally jumped up and down on it and it will not move. Which is great, because if you have a medical robot and someone's arm is in it, you don't want, people walking by, like a particularly large person walking by, and suddenly they're getting poked, right? Anyone in the 218 loft, have you noticed that when large people walk by, everyone's robot oscillates? Okay, so let's talk about this. Anyone know what this is? It's a big mass that I can bolt stuff to. What's the term for it? An optical table, or an optical breadboard. A breadboard, like in electronics, because I can prototype things easily. If I want robot A here and robot B down there, I can adjust their offset. I can do anything I want on this. Okay? Now this is freaking heavy. Oh, my back! Okay, so one thing is it's nice and heavy. The other thing is it's ridiculously stiff. So robot A and robot B are going to be rigidly connected to each other, and because I have tapped holes everywhere, I can move them around at will. Cool. How are you going to move your robot? You will have to move your robot. Even if you build it at your desk in your PhD lab, You're going to move, I don't know, some of you are in different research labs, you're all moving right now. Allison's lab, and David's lab, and Kokoski's lab, literally every single lab is moving 2 or 3 times in the next years as they play musical chairs with buildings at Stanford. So you will move, just because they're going to tear down your building. Also, because you're going to start collaborating with people in the hospital and they're going to want you to bring your robot into the OR. Or you're going to collaborate with the psychology people and they're going to want you to bring your robot into the fMRI scanner. You're going to move your robot. You don't have a choice. So, how are you going to move it? If it's heavy, you need a pallet jack. Those are like $300, they're cheap. I could have another person on the other side lift this. What's going to happen if I have a bunch of counterbalance stuff and I start lifting my robot? It's the PR2 on us. So you need joint locks for the sole express purpose of moving your robot. Anything that's going to move when you move the robot has to have a joint lock on it. Now say this is ridiculously heavy and I was dumb. I didn't put a frame on it. I just have this on a tabletop and it's too heavy for me and it's too heavy for 2 people and 4 people can't fit through a doorway. Then what do I do? At some point I can't pick this up. Say it takes 20 people. I don't want to disassemble, that's a pain. Anyone heard of an engine crane? So that's how they move car engines around the factory. It's an engine crane. It's simply it's got wheels, and then it comes over like this, and then there's a little loop on a chain, and there's a hydraulic lever, and you can raise and lower this at will. So you lower it under your robot, and then you crank it up, and then it's supported, and you move it very slowly. Okay? How do I connect that to this? Straps or hook. You have to design that in. So make sure if you're building large robots that you put in, they're called, well, strap you don't really need to design that much for, but just figure it out and put it in your CAD. Also latch points for things like engine hooks or whatever it is. Maybe you don't need an engine crane, but for me I've had to think about these things. Even in the machine shop, I had a board just like this machined, and they were like, most of the shops couldn't do it, and I quote, "We don't have the manpower to lift it," just like around the factory. They didn't have an engine crane. So I put in some special holes so that they could use the equipment they did have to move my board around the machine shop. So this is real stuff. Okay, do you want to make these? No, you don't want to make these. These are really expensive. Every time they have to drill and tap a hole is time, and time is money for them. So however many hundreds of holes this is, they don't want to do this and you don't want to do it. Buy these. The 1/2-inch ones about the size on, it's either Edmunds Optics or Thor Labs. They're about $1,000. If you're here for the long haul and you're doing a PhD dissertation, your advisor needs to buy you one, because otherwise you're going to spend weeks dealing with your robot vibrating or trying to lift it or being like, why are my 2 robots at weird angles and keep vibrating? That is money very well spent. Another thing, has anyone seen me taking the cart to and fro before and after lecture? Has anyone seen me very carefully trying to pick up the cart as I come over the door jamb? You want to design for how you're going to move robots past door jams, through doors, past elevators. If you have a small robot, it's not that big of a deal, but even a small robot on a big table is still a pain to move through a door. Just try it. Take a tape measure, measure the door, width, height, the elevator height. Pick a plan if you're going to the hospital for medical collaboration so that you're not going over tiles. They very dumbly tiled every surface in the Clark Center outside. And actually I took my IV robot from downstairs to up here for a clinical experiment, and the damn thing decabled due to the vibration. So every ka-clunk, 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 ka-clunk loosened the screws on my cable cap stands, and then it randomly fell over because the cable fell off. So you might even want to, if I was going to put that on a pallet jack, I put a 1/2 inch of carpet or foam in between the pallet jack and that, because it dampens out that vibration when I go past tiles. I know these seem like trivial details, but it's the difference between your robot working and not. We're almost done. Are there any questions about 80/20 or how to, optical breadboards or how to move them?
you get 80/20 only in aluminum or?
It's all aluminum. If it's out of steel, you're too heavy. Oh, also, the inside of these can be used as pressure chambers. So you can actually transmit pneumatic signals and power through the middle of them. Just keep that in mind. If you put an in plate on, you can tap these holes, and then you can put a little gasket, and you can use these as pressure, like cylinders. Okay, any other questions? Okay, so what's coming next? Basically, I was going to talk about springs because I'm always there. Always going to talk about springs. I think you actually do need to see them on Monday, mainly for the in-stops. You were all 5 minutes late. Okay, just real briefly. What we're actually 100% sure going to talk about next time is springs. Yeah, I've already told you about counterbalancing, so I'm not that interested in telling you more about that. But does anyone know what in-stops are?
I was just going to say, I think, I'm not sure if you got the email, but the founder of Spline will be here to give a
Yes.
talk before 5.
Exactly.
So,
I don't know, it's up to you. I have to lecture, and I take attendance, but it's up to you guys. I would personally like to go and see it, but I have to teach. So.
We start class at 5:30.
yeah, can we should,
Can everyone make it after the talk?
it's the founder of Spline that basically selling without building equipment and like breadboards and like servos and motors and stuff like that. And you're going to be here for the first class.
If we started class at
4:15.
what time is it let out?
5:30.
5:30. If we started class at 6, could anyone make that? 6 to 8. How many can't make it? Show of hands.
I mean, that's what I was just putting out there, like whether or not
I probably.
people in the class are interested in going, but if not, then like I'm not asking.
How many people would like to go to the talk? And I don't mean because you just heard about it, but you had been planning on going to it. Show of hands. I think that's more than can't make it. So I'm probably going to lose all of you anyway in terms of you're not going to show up. So okay, we'll move it. So we'll start class at 6 on Monday.
Presentation's not going to be recorded.
Any objections?
And this class will be recorded on Monday night.
Yeah. So it'll be from 6 to 8.
So couldn't we just do class at the normal time and people who miss it for the talk can watch the recording?
We could also do that. Okay. Want to flip a coin? Somebody call heads. What's heads? I heard like a bunch of stuff. One person gets to talk for the group. What's heads?
6.
Class at 6 is heads?
Yep.
Heads.
Just 2 and 3.
Heads. Here, you know what? Someone else do it because you're all going to accuse me. You flip it. Best 2 out of 3. Heads is at 6.
Gravity's different. Tails.
Okay, and one more time.
Tails.
Okay, so class at the normal time on Monday. Those of you can be excused if you're going to Spark Fun. If I see you out there sipping coffee and not going to Spark Fun, I'm going to be pissed. And if you are absent, then you can watch it on YouTube. You took my last 5 minutes. I was going to talk about springs. It's okay. The only time. That's it. Screw springs. We're not covering them this quarter. We're done. Office hours at